you a brief summary for previous class. I believe you already have some pictures about what's the kinetics. So kinetics is a time-dependent state change process for a system out of equilibrium, and the path and the corresponding rate allow this deviated allow these systems deviated from equilibrium back to equilibrium process is what we are interested in, is we call the kinetics process. And what factors will affect the kinetics process? The first one will be the driving force. The driving force applied on the system. And the second one will be the transport, the inertia of the system, or you call it is a transport resistance or transport mobilities. Let's take an example. For the mass transport, the driving force would be the chemical potential gradient, and the inertia of system, or you call the intrinsic material property, which affected this kinetics to effect the mass transport probably will be the diversibility. And if now we talk about the heat flux, the driving force probably is the temperature gradient applied in the system, and the inertia of the system or intrinsic of material property would be the heat flux would be thermal conductivity of this material. And if we talk about the electrical current flow, the driving force probably is electrical field or electrical potential applied on the system, and the inertia of the system probably is the conductivity of this system or these materials. So my opinion is, in any you're interested in kinetics process, you need to find out the driving force and corresponding of inertia of the system. Then you can determine the rate of this kinetics process. And next we talk about related to the thermally activated process. That means you didn't apply external driving force on the system, just put your system at the surroundings. And these materials or these atoms only have thermally activated process depending on the surrounding temperature. Then we can estimate how many atoms have the certain your interesting energy by using the Maxwell-Boltzmann distribution. And the thermal energy usually we put will be the KT. So if you put the KT here, then you know the roughly the atom distribution within this system. And regarding to the rate determine the process. In kinetics process, you need to determine is this kinetics process is a single step process or it is a series process. For example, like a melting process. Melting process is like the material or atoms should absorb the heat from surroundings or from somewhere, then have energy to do the migration stuff. So it would be the heat flow process or the heat absorption process, then mass transport. So it would be the series process. And your kinetics process is parallel process. For example, like the catalyst process, like if there's a chemical reaction and with a certain energy barrier, then after ending the catalyst, we can provide the other path with lower activation energy or lower energy barrier to allow our reactant converted or generated to our product. So in this system, the atoms do see the two paths with different activation energy. So that we say is a parallel process. The rate determining process in serial process would be the slowest one, and in the parallel process will be the faster one. So we need to decide what kind of process we are dealing with, then we can calculate or estimate the rate in your kinetics process. Okay, so let's move to the section 2. We are going to show you what's the thermodynamic equilibrium state and what's the steady state. Thermodynamic equilibrium actually, it helps us to define the state function. So state function is defined at the equilibrium conditions by thermodynamics. So how can we determine if our system or whether our system reaches thermodynamic equilibrium? It must satisfy the following two criteria. The first one would be the same chemical potential everywhere in space. There's no spatial variation in the system. So that tells you that the chemical potential gradient equals to 0 because the chemical potential anywhere are the same, right? So the second one would be the free energy. The total free energy of the system must be minimized in this closed system at the equilibrium conditions. So any movement of this atom or any movement adjustment on this system will increase the total free energy. So a system reaches equilibrium, the first one definition would be no spatial variation in chemical reaction. So that means there's no net mass transport. So as we mentioned before, the atoms always move around anytime, any moment. So sometimes the atoms jump to right. Probably if less 3 atoms jump to right, then most 3 atoms jump to left. That will result in no net mass transport. So now no net mass transport doesn't mean the atoms just stay there. They still keep move around. Okay? And the second one is the total free energy is minimized. So that means any movement will raise the free energy of the system. So this is two criteria when we describe the thermodynamics equilibrium in your systems. So next slide, we are going to give you the two examples and hope you can tell us if whether these two cases, the system of these two cases is reaches thermodynamic equilibrium or not. The first one is now if we have a curved solid materials. Do you think this system or this curved solid material reach thermodynamic equilibrium? In order to answer these questions, first of all, don't forget the definition or criteria for thermodynamic equilibrium. The first one talking about the chemical potential, if there's any variation in chemical potential. So let's put here, we need to know if there's any chemical potential variation. So if now we have atom A here and atom A here also, and the chemical potential of this atom located at the convex side can be expressed like this. It's phi AS means the chemical potential of atom A at the surface can be expressed like the mu A0. That means the chemical potential of atom A at the flat surface. And because now it is not a flat surface, so we need to add the modify extra term. And this term is related to the gamma is a surface energy, omega is atomic volume, and times the curvature kappa 1 plus kappa 2. Then this we know if not this is the chemical potential of atom A at this convex side. And if we want to write down the chemical potential of atom A at the concave side, can be expressed like this: is mu A0, the chemical potential of atom A at the flat surface. Because now it is not the flat surface at all, so we need to end it. Modified term is minus gamma is a surface energy, omega is the atomic volume times the kappa 1 plus kappa 2. And kappa 1 and kappa 2 also the curvature to describe this curved surface. So now we find that the atom at here, the chemical potential of the atom here and the atom here is different. So there must exist a spatial variation in chemical potential. So based on this, we know this material system is not thermodynamic equilibrium. And this curve, this picture I grab here is just want to show you the relationship. What's the kappa 1, kappa 2? So in order to well describe the curved surface, in engineer mathematics, they tell us that you need to use the curvature kappa 1 and kappa 2 to well describe the geometry of a curved surface. And the curvature is usually a reciprocal of the radius. Okay, so if you look carefully, yes, there's a variation in chemical potential, right? And the purpose, don't forget, is the system always go to the total energy of the system always get smaller and smaller. So the driving force in this system will be minimize the surface chemical potential. So the atom now here with a higher chemical potential. Why? Because we plus the positive term. And this atom here with a lower chemical potential because we minus a positive term. So the chemical potential here is a lot higher than at here. So because in order to minimize the surface chemical potential, this atom must be pushed toward here. So you will observe a flux J toward this direction, and that will result in the surface planization. But this is based on the energy point of view. So how much time it takes to reach the surface planization, that depending on the kinetics process. So we need to calculate that. But based on the energy point of view, you can determine the direction of the system. It must be surface planization because the atom here be moved toward concave side and resulted in the flat surface. And the other case will be the grain growth. During the grain growth process, you can observe in the beginning it is a polycrystalline film. And during the grain growth process, you can observe some grain get larger and larger. And some grain, like this grain, shrink, get smaller, and disappear. So during the grain growth process, we can observe some grain get larger, some grain get smaller or disappear, and the driving force is minimize the total energy of the system. And in the polycrystalline materials, the total energy is dominated by grain boundary compared to that in grain. And even we assume the isotropic grain boundary energy. So during the grain growth process, the volume of the grain boundary decrease, and that will result the total energy of the system decrease in the meantime. So this process also is not a thermodynamic equilibrium process, it's a kinetics process. So I believe you already have some pictures about what's the thermodynamic equilibrium process and what is the kinetics process. So now we move to the definition for equilibrium state and steady state. So based on what's the equilibrium conditions, our state function, f is a state function. State function partial f partial t equals to 0. This tells you that the state function do not change with time at the equilibrium condition. And also, there's no driving force applied on the system. Because there's no driving force, so if you consider the mass transport, no driving force, that means there's no chemical potential gradient in the system, so no mass flux. If we talk about the heat flux, so there's no temperature gradient in the system, so we cannot observe any heat flux. So we call it this kind of condition, we call it the equilibrium condition. So state function do not change with time and no driving force exists in your system. And how about a steady state? Consider a steady state. The state function also do not change with time, but sometimes it probably change with location. As we mentioned in previous slide, like a metal bar, and we put the heater and the cooler. Heater at the left-handed side and cooler on the right-handed side, and it reaches steady state. We can observe the temperature distribution along this metal bar, right? Something like that. But in this steady state, you can observe the driving force exists or apply in your system. For that metal bar, there's a temperature gradient, right? It serves as a driving force. So because there's a driving force, so there's a constant driving force, then that will result in a constant mass flux, constant heat flow, because there's exists of constant driving force. So the system probably have chance to reach a steady state. As long as we remove the driving force exists in this system, then this system will go from non-equilibrium state, or you can call it as a steady state toward to equilibrium state. So that's what we call a steady state. State function do not change with time, but however, you can observe the driving force exists. Some people ask about, is this a constant driving force? So we got the constant flux. How about if a time-dependent driving force? So we will get the non-steady state. So non-steady state just tell you the differential equation will be the time dependent. That means the concentration or the temperature distribution profile varied with time. Okay. So by the way, I can give you an example about the non-steady state. Non-steady state means the driving force varied with time. So if we take the metal bar as an example, in the beginning, the metal bar, because of the heater and the cooler, that will result in a steady state of that metal bar. Then you can observe the temperature distribution along that metal bar. And this profile do not change with time, right? But however, if you remove this heater and cooler, then this metal bar will the status of this metal bar will reach equilibrium, and this process we call a non-steady state. Because the driving force vary with time, right? The driving force here in this case is a temperature gradient. So as long as I move the heater and the cooler, the temperature gradient will get smaller and smaller until it reaches equilibrium with the surrounding temperature, right? Okay, so this is a non-steady state. Okay, so let's talk about more about, let's talk example, heat flow in steady state. Although this example we already mentioned before, but we can just take this as an example. Now we have a metal bar, and you put a heater here and a cooler here. So there's some heat input in this metal bar, and also the cooler will take some heat out. And we measure the state function temperature as our indicator, and also use the thermocouple to measure the temperature profile along this metal bar. Then assume in the beginning, when we ended the heater and the cooler on heat, the Q in and Q out may not equal. But after a while, as long as the Q in equals to Q out, the system will reach a steady state. That means the temperature profile on this metal, measured on these metals, do not change with time. And based on this, we define what's the local thermodynamic equilibrium, right? Because this profile do not change with time. So if I look at this location, the temperature, the state function do not change over time. So we call it as a local equilibrium, thermodynamic equilibrium. So that's why we can apply all the state function or energy we derive from thermodynamics in kinetics, because we make this local thermodynamic equilibrium here. Okay, so in this case, heat flow in steady state case, the heat flow do not bring the system from one state to the other. No, because the temperature profile do not change with time, but you did observe there's a driving force, the temperature gradient exists in the system or apply in the system. So this is a steady state. And in order to confirm if these conditions, this condition does satisfy the criteria we mentioned in steady state. So let's check each one. The steady state the state function do not change over time, with time, so yes. And less driving force exists. Yes, because there's a heater and a cooler, and the temperature gradient serving a driving force keep the same, right? The driving is a constant driving force because the temperature gradient is the same during this process. So the driving force exists. And when we remove this driving force, that means we remove this heater and the cooler out, then the system, the temperature will reach to equilibrium. Temperature will the same with surrounding temperature, right? Okay, so this is, if you check this one, yes, so definitely this situation or these settings is a steady state because it satisfies all the criteria we mentioned in steady state. And by the way, some people were concerned about, in reality, can we really measure this profile? Some people were concerned about the thermocouple, which we use to measure this temperature profile, because this is a heat flow, right? The heat flow is going to flow through this metal bar. But however, there's a thermocouple, which we use to measure the temperature profile. We also observe some tiny amount of heat, and to interference the heat flow, it flow through the system. So yes. So in reality, if you want to get this profile, observe the phenomenon of steady state, you need to use the tiny probe of this thermocouple and avoid the heat loss due to from this thermocouple. Otherwise, the results you measure will be a bit different with this results. So here, in order to make it perfect, so in our textbook is just make an assumption like we ignore the heat capacity of this thermocouple we used. Okay, so just mention that. Okay, so so next we are going to show you what's the difference. Can you we'll describe the difference between steady state and non-steady state quantitatively described in mass transport. So as we know, the steady state is there's a constant mass transport under constant driving force. So you can get, I want you to plot the concentration profile in this mass transport or diffusion, you will get the time-independent concentration distribution in your system. But however, so how to do that? So based on the continuity equation, or some people will call it as a mass conservation law, steady state means that partial C partial T equals to 0. C here is a concentration of diffusing atom. Means the concentration profile of diffusing atom do not change with time. And steady state means less a concentration gradient exists in this system. So based on continuity equation, you can formulate like this. Partial C partial T equals to negative divergence of the flux. And based on Fick's first law, you can get the flux J equals to minus diversibility concentration gradient. So minus becomes positive. So you got this one. And because steady state, so concentration do not change with time, so it can get 0 here. So we can, based on here, we can solve the C concentration profile, right? So make an assumption. If the diversibility is constant, you can pull this out. Diversibility, then you can get the, and because it do not change over time, so you can drop this parameter. So you can get this diffusion equation for steady state. And as long as you solve this diffusion equation, you can get the C. C is a concentration of diffusing atom. You can get this distribution profile of the diffusing atom along your materials. And how about if your kinetic process is related to non-steady state diffusion process? So non-steady state means the time varying mass flow, and also is under the time varying driving force. So everything is time dependent profile. So you know the partial C, partial T is not equals to 0, and also there must exist a concentration gradient. So when we also write down the continuity equation, and the J is we substitute with diversibility concentration gradient, because this term is not equals to 0, so we need to solve this diffusion equation with 2 parameters, and also assume that diversibility is constant, so we'll pull this out, and you got this diffusion equations. So for the non-steady state, the concentration profile of diffusing atoms will be changed with location and time. But for a steady state, the concentration profile of diffusing atom only changes with location. So as long as you solve this diffusion equation, then you can get the concentration profile during your diffusion process. So we will talk about this in detail in chapter 3. Just give you some pictures and focus on the time-independent steady state or time-dependent non-steady state. Regarding to the continuity equation, so there's a way to help you to remember or derive this continuity equation for mass transport. Okay, so if I put our interesting system here, or interesting material bulk here, And this is x, and this is x plus delta x is a location. And the area here is the A, and I do have atomic flux or a flux here, and also flux in this system, and also the other flux out of this system. So because this flux is like at this x delta x. So what's the continuity equation, or some people call it as a conservation law? It's like the if I am a system, so I get flux Jx, I gain some flux, but I lose some flux. This flux is out of my system, right? And if I times the area, so this is the how many atoms left inside this system, right? Because of flux, the unit for if this flux is a mass flux, so it's a number of atoms per area per unit time period. So you times the area, that means the will be the at per unit time how many atoms now is left inside this system will be equals to what? The concentration change times the volume of the system. So the volume of the system here will be the A times delta x. If we check the unit, the concentration is what? Is a per volume per number. I mean, how many atoms is the numbers of atom per volume, right? So if you times the volume, will be left the numbers. So, right? So it's perfect. So if you just simply divide it, if you just delete the A and just simply move, let me Jx minus Jx and move the delta x here, partial C, partial T. And what this is actually is minus flux gradient. So this is a continuity equation. Continuity equation here in mass transport is like the partial C, partial T. The concentration change per time equals to the minus divergence flux is what would look. Okay, give you a short summary about the equilibrium state and steady state. The equilibrium conditions means the state function do not change with time, and there's no driving force existing in this system, and this conditions is defined by thermodynamics law. So in this kind of situation or system, you cannot observe any net flux. However, in steady state, yes, the state function also doesn't change with time, but we can observe a constant driving force exists in your system. So constant driving force, so you can observe the constant driving force. And based on this, we need to assume it's locally thermodynamic equilibrium, and we will get the time-independent diffusion equation, and you can get the concentration profile do not change with time, but change with location in your materials. For the non-steady state, the state function do change with time, and so is the driving force. So will be the time varying driving force. So based on this diffusion equation, you are going to get that the concentration profile of diffusing atom changed with location and time. Okay, so this is a short summary and the difference between the equilibrium state, steady state, and non-steady state. Okay, in this slide we are going to show you how can we expect or estimate whether our system will toward to equilibrium or steady state. So before that, we need to you need to have some pictures about the term we call the irreversible thermodynamics. Usually, in thermodynamics, we always talk about a reversible process. That means every change we made is a very tiny change in no matter it's the pressure or the volume in thermodynamics, then the reaction or the system states can reverse to previous state easily. We call it is a reversible process. But here, as we know, the steady state or non-steady state, any kinetics process is irreversible thermodynamics. So what's the irreversible thermodynamics? Let's actually try to apply the thermodynamics principle to describe the systems which is deviated from equilibrium state. So then toward either to equilibrium state or steady state. So let's make this simply. It is we need to expect or estimate our system will go to either equilibrium state or steady state. Are there any ways to predict that? Yes. If your system is in homogeneous boundary condition, that will drive your system toward to equilibrium conditions irreversibly. For example, homogeneous boundary condition means now in the beginning we have a metal bar and we put the thermocouple to measure the temperature at this location, expressed like a T bar. Then we ended the same heater with same temperature to the end of this metal bar. This we call is a homogeneous boundary condition. In this case, after a while, this metal bar will reach the temperature of this metal bar will reach Th, the same with the heater, the same temperature with the heater, and that will reach the equilibrium condition. So in homogeneous boundary condition, in this kind of case, that will drive your system toward to equilibrium condition irreversibly because you cannot move back without additional and extra energy. And the other case in your textbook called inhomogeneous boundary condition. That means the system will go. That means what's the inhomogeneous boundary condition? The same. That means we also have a metal bar, but we put the heater at left-handed and put the cooler on the right-handed side. Then, after a while, the system, when the Q in equals to Q out, then the system will go irreversibly to the steady state. That means the temperature profile at this location do not change with time. We call it the steady state or local thermodynamic equilibrium condition. So the boundary condition, different boundary conditions will lead or drive your system toward to equilibrium or steady state. And if you provided a driving force, or you call the inhomogeneous boundary condition, then you will drive or push your system toward to steady state instead of equilibrium. But if you provided this Th is the same, the heater with the same temperature, there's no driving force, right? Then you push or drive your system toward to equilibrium state. And I will give you the other example related to ideal gas. Ideal gas always obey the ideal gas law, which is the PV equals to nRT equals to constant. So if you plot the V versus pressure, the volume versus the pressure, then you got the black curve. And each state listed on this curve, black curve, is equilibrium condition. And also, if you want to move from state 1 to state 2, then it's reversible. Or state 2 to state 3 is reversible. Right? But this is what we call equilibrium condition. But what's the irreversible or kinetics process? Is we try to use external force to increase the pressure, then we can get to this point. Then we release this pressure. Then the state of system will drop back to this equilibrium condition. Then we apply the other driving force to increase the pressure again. Then the system will toward to equilibrium condition. From the non-equilibrium or deviated conditions toward to equilibrium conditions. The same thing we repeated. Then the blue curve represented is the irreversible thermodynamics process or irreversible process. If you don't want to increase the pressure, you also can play with the volume. If we use the external driving force to decrease the volume, then the system will move to equilibrium condition irreversibly, then decrease again, then move back to equilibrium condition, then the purple one also irreversible path. So this irreversible path involves the external driving force. Exists the external driving force to push this system away or out of equilibrium, then release, then back to equilibrium. So we got this irreversible path. So we normally call a steady state as an irreversible process because during this process with this subject to external driving force. And what's the equilibrium conditions or reversible thermodynamics is if the change of the pressure or the volume is very tiny, it's very small. That means the dP and the dV is very tiny. It's near zero. It's very tiny change. Then the path will obey or follow the reversible process on this thermodynamic equilibrium conditions. Okay. So I will give you a short summary for irreversible process. Irreversible process is always happens from where? From out of equilibrium condition toward to equilibrium conditions and irreversibly. And homogeneous boundary condition means there's no external driving force will lead your system toward to equilibrium conditions irreversibly because the system condition cannot move back, so we call it irreversibly. And regarding to the inhomogeneous boundary condition, that means you apply the external driving force in the system, so that will push the system toward to steady state irreversibly. So that's what we're interested in. We call it flow process. So it's not that hard to remember all the relationship here. Is like if we have a metal bar and just put it in here, and T1 is the temperature of surroundings. So now this metal bar is at the equilibrium condition, and we ended the external driving force to the end of this metal bar. Then that will drive this system toward to steady state irreversibly because this state cannot move back, right? And so this is irreversible to steady state because the temperature profile does not change with time, but it changes with location. Some people ask me, Ying, or Professor, how about if I move the heater and cooler out? Then the temperature profile it was here like this, right? And it will go back to this, and this process is also irreversible, but because we don't have driving force, and we don't have a constant driving force, but the process during this process the driving force varied with time, right? Because the temperature along temperature difference or temperature gradient apply of this metal bar decrease over time and until it reaches the uniform temperature T0. So this process is is non-steady state irreversible process. Okay, hope it